Good evening, everyone. So I'll be sharing today or discussing related to the recurrent neural networks, which is another important part of this subject, DRL, deep and reinforcement learning. Because deep learning, there are two flavors we are going to study in the whole subject. One is CNN, which has been studied also with the pre-trained models, operations of CNN and other things. And also at the end of the last class, I have discussed on recurrent neural network. I will just start with that and then discuss few other important mathematical things related to the recurrent neural network. So first, let me share the screen. Okay. So let me go to the presentation. Yes, as you can see, there are usually two types of networks, recurrent neural network and the conventional feed-forward neural networks. The important thing is whenever the inputs are given and the output is being produced, it will also remember what output it gave. Okay, that is what you can see in this graph. There is a loop. Okay, here just for an input, some output comes based on the input weight, convolution, operations, all those things. Here, it also remembers through some concept called as hidden state. Okay, so coming to the recurrent neural networks, given an input xt, that is input at a time t, input x at the time t, it will go through the hidden layers, and every time it goes to the hidden layers, the output will be stored. Okay, and finally, output y at the time t is produced. This is like a black box, but if you unroll this is called rolled RNN, means the black box version. Behind the scene and details, we are not bothered. You give an input, you get an output, and the hidden layers will be called multiple times, and finally you get the output. That is what we see as a black box, and that is called a rolled version, just like you roll the mat. Okay. Now, if you want to go through the detail, actually what is happening inside, this is what happening inside, exploring inside. Just like you bisect some insect or something and see what is there inside your botany experiments or zoology experiments, sorry. Here also, we are going to bisect and we can see that there is an unrolled RNN which gives us what is happening behind the scene. The input xt is going to come as x0, x1, x2. And the input at the time t will not directly come. It will come in sequence. Many examples, like I am speaking something. So every time my words are changing. So every time the new words are arriving, you may have to convert that into text. Then time information is also important. Language translation, that is the project. Or even the chatbot. At the time t, some question was asked. At the time t plus 1, some other question will be asked. Based on the context, some other questions will be asked. So all these applications, they not only have to see the data, they also requires the time data at that time. Not that always data, it is the data at that time. So the input x at the time t actually is a sequence of the inputs x0, x1, x2, etc., etc. Now, what is happening inside is whenever you go through an input x0, it goes to the hidden layers, and whatever output comes is also fed to the next hidden layer. It's not just producing the output as y naught, it will also send that to the next hidden layers. And the cascadingly, you are sending to each hidden layers. And you're remembering that output, what you produced. They're all required. Memory is required, particularly in the our any of the text applications, whether language translation or whether generative AI, is text generation, text summarization. All these things, they need to memorize what they have produced earlier. Suppose that one whole big paragraph I'm summarizing, then what I had at the beginning, what I had at the middle also is required when I'm concluding at the end. Okay. So this is the unrolled version of RNN. That is, the input comes as a stream at the different instance of time. And every time an input is given to the hidden layer produces the output or gives to the output. Also, it feeds to the next hidden layer. See, there can be a connection. This is only one connection we have shown, hidden to hidden connection. The recurrence is there with hidden to hidden. That is hidden layer not only giving that information to the output and producing something, it is also feeding that to the next hidden layer. Some sequencing is going on. Then that second sequence hidden layer is giving to third. Third is giving to fourth, like that. So that is the unrolled version of the RNN. So there may be a question on what is unrolling. You have to explain both rolling and unrolling with this diagram. Next. Lot of applications of RNN, I think that also I told, basically the chatbots, whatever chatbots we design or whatever the virtual assistants we design needs RNN. Then auto completion. In the email, you might have seen you type something, automatically something gets completed. Auto completion or predictive text applications. Financial, if you take the stock market, you want to predict how will be the share and other things. So we can use this. Anywhere time series analysis is there, it is helpful. So you want to do intelligent traffic prediction. There also, what is the traffic right now and what is the traffic after 2 hours? There again, RNN is required. Or if you're doing some AI work for call tracking or you want to design it for 6G, 5G, like that, there again, that the time series analysis is required. And wherever time series analysis is required, invariably we have to use recurrent neural networks. Okay. Medical diagnostics, you are given a complete pathological report, radiological report, and you have to do analysis. You have to read completely. There again, it is required. And video analysis. Video, because we have to, for example, one simple application is you are given a complete video of the game. You have to generate highlights. 2 hour hockey match is given to you, or 1 hour hockey match is given to you. You have to generate a short 10 minutes highlights. Then complete time series it has to take. And whichever is important, it has to start building. From that, important things has to be taken and the highlight has to be generated. And of course, the very popular, powerful language translation from any language to any other language. If you want to translate English to Kannada or Urdu or Hindi, something, definitely RNN plays an important role. Okay. Because when you're generating the equivalent words, you need to see the context. You can't do it transliteration, word by word, character by character, cannot do. You have to see the context and you have to produce. There, all these applications, RNN is required. So you may get a very simple question. Give or explain the different RNN applications. Explain when they ask every application you have to take and tell how RNN is used there or why RNN is required there. And when you are explaining why RNN is required, two things you have to mention. It is a time series application and it requires memory. You take chatbots over the time, the chat sequences change. And what I chat earlier with you also I have to remember. So both time and memory, both are used. Predictive test or auto completion, I have to see the context what you're typing. Based on that new I have to give you. Okay. Earlier what I have given, I should know. All those things. Earlier what I generated also I should know. And based on the time, it has to start giving the information. So all these places, RNN is used, recurrent neural networks. Next, if you compare the, maybe another very standard question, differentiate CNN and RNN. Architecture-wise, CNN uses convolution layers to extract the features from the data, whereas RNN uses the recurrent layers. Okay. And it has to process the sequential data. 1 second. Okay. And where it is used, CNN primarily for image recognition and computer vision, whereas any NLP and any time series analysis, you require RNN. The major difference between CNN and RNN is the data input is fixed size, input fixed size output. Here you will have variable size input, sequential data, both, which is not found in the CNN. Memory definitely is not useful in CNN, whereas RNN basically uses memory in the form of hidden states. It will memorize what I generated intermediate stage. It will memorize, and that is the hidden states. Hidden layers is different. Hidden state is different. Remember that. And parallelization, unfortunately, the major drawback as far as RNN is concerned is you can't parallelize it, as it is a sequential data. It is basically built for a sequential data. You can't parallelize it. It depends on the previous one. Okay, first to second data will go to second, second in the third, third in the fourth. You can't parallelize 1, 2, 3. One after the another only the sequence happens. Okay. So video I was talking about. You have to build video highlights. You have to go through from first second of the video to the so much minutes. You can't take different segments and then try to build the highlights, because there will be a link from one to another. That's a problem. One second. Yes. Sorry. Somewhere here. One second. Yeah. We finished on the applications, and also we differentiated the CNN and the RNN. Okay. Next. This is one topic called as unfolding computational graphs, where you have to find out what is a computational graph and then see how to unfold it. Now, whatever happens mathematically inside an RNN has to be expressed as a graph. The computations that happen inside RNN has to be expressed as a graph. Graph means nodes and edges, as you know. You have to express like that. And such graphs are called as computational graph. And we have to elaborate it and explain. Not that summary or the black box we have to give. We have to give complete picture, elaborate what happens inside. And that is what unfolding. We will see all these terms, unfolding computational graphs, particularly in the context of RNN. Now, this is a way to write the computational graph. If you see the left part, that is A, neural network. Normally, any neural network you take, you will have the different inputs. On that, weights are applied, bias is added, which will decide what is the next hidden layer. Okay, epsilon is the hidden layer. Now, as you can see, the mathematics going in the feed forward, what is that? P is equal to Wx. So first, whatever the inputs are there, you have to multiply the weight, which will decide which input has what role to play. And on that, some activation function is applied, G of P, which gives us the hidden, which is epsilon. Computationally, what happens, if you see this middle one, computational graph, then we have W and X, where W is the weight, X is the input. You multiply, this is X is multiply operation. You get P. On that, you apply a function G where you get epsilon, which may be the output. You apply some activation function, finally you get some output. Now, the problem with the output is there may be some error in that. There may be some error in that. What is the error you may have? Say epsilon you get some error. Otherwise, the actual may not be matching with the predicted. Then we have to inform back that you have to update your weights. That's what we do normally, back propagation. So instead of informing the error directly, we take the gradient of the error, that is the partial derivative, and that is what you are doing there. If you want to do the partial derivative with respect to W, that is here, backward propagation, we multiply it by two things, partial derivative with respect to P, which is actually Wx, the partial derivative of P with respect to W. These two cancels, you will get delta E by delta W only. Now, delta E by delta P has to be calculated first, then delta H has to be communicated back. And to W, what you have to communicate? Delta P by delta W. To X, what you have to communicate? Delta P by delta X. They are communicating back three gradients. One is the error with respect to P. the other P with respect to the input, P with respect to the weight, because P was found with W and X. They're informing that these are the changes you have to make. Okay, so then the things will happen. This is our normal feed forward operation and how a computational graph is written. So in this graph, clearly the computations are shown, both feed forward and back propagation, both is shown. Feed forward, what is going on? X and W is there, you're getting P. On that you apply G, you get some output, which is, of course is an error, epsilon. So error I have got, I have to improve myself. So we are going to communicate back the gradients, which is the back propagation. So we are informing first P with delta E by delta P, then to the W and X, P by W, P by X. Fine. This is the actual graph, computational graph. In the case of feed forward networks, that is CNN, there will be a small change when I go to the RNN. What RNN says this, the state at any time t is actually a function of the previous state and theta. Earlier, we were only using theta, that is W and B. You go to the previous example, only weight was there. Actually, practically, weights will be there and bias will be there. With the input, you multiply with weights as well as bias and then go to the next layer. But what RNN says that if you want to determine any state, S of t, any state at the time t, it is a function of the previous two things, previous state and theta. Theta and the weights and biases. So previous state is also required. Theta and that is bias and weight is also required. You can't only do with bias and weight. You also need previous state information. So if I want to find S3, I should know S2 and theta. If I want to find S2, I should know S1 and its theta. Recursion is going on there. S3 in the, if you want to find S3, you should know S2 along with theta. S2 ಗೊತ್ತಿರಬೇಕಂದ್ರೆ S1 and theta, like that. Small change in the recurrent neural networks, and graphically it looks like this. If you want to find S of t minus 1, what is the previous state? S of t minus 2. S of t minus 1, if you give apply f on that, it will find out S of t. S of t in the, you can find st plus 1. From there you can find st plus 2, like that. It goes on. Okay, function f is there. Theta, that is weights and bias, is there. Along with that, previous state is also required. That is what happening in the diagram. Next. Now, they are giving more information. That is not just that the previous state is required, not just the weight and bias is required, also what is required, the input at the time t, the xt. So S of t, in more clarity, requires three things. The previous state information, S of t minus 1, previous state, the current input, and the weight and bias. Now that is called hidden state. Hidden state at the time t is determined by hidden state at t minus 1, the current input, that is the input at the time t, and theta. Theta means weight and bias. So unfolding, that is normally what we say, from the x we apply to the hidden and store it back so that we can use it for next time. Here, the hidden at t minus 2 will determine t minus 1 along with xt minus 2. If I want to find ht, what is required? Ht minus 1, xt. If I want to find ht plus 1, xt plus 1, and ht. If I want to find the hidden state at a particular time, I need the previous hidden state and current input. Previous hidden state, current input. And this goes one by one only, sequence. Unless you find ht, you can't find t plus 1. You can't find t plus 2. It has to go one by one only. You can't parallelize it. Okay. That is unfolding. Unfolding is clearly showing what is going on. The hidden state at the time t is determined by previous hidden state t minus 1 and the current input xt. It's a function of these two. These two are given to a function which finds out the value of the next hidden state. So the difference between the computational graphs is earlier only weight and bias and the input was required. Now the previous hidden state is also required while computing in RNN compared to the conventional feed-forward networks or the CNNs. . 。  . 。 . 。 . . . . 。 . . . . . 。 . . . . . 。 . . . . . . 。 . . . . . . . . . . . . . . . . . . . . . . . . . 。 . Okay, that is about one topic. Next one, how to create the computational graphs in RNN. Various cases are there, how to unfold. One of the case says that, as we have already taken, uh, if you want to find the hidden state at t minus 1, you should know the previous state and you should know the current input. Remember how not just the inputs and the hiddens, they are actually scaled with some values. Like hidden is multiplied with the previous hidden is multiplied with w, current x is multiplied with u to get the current hidden state. The hidden state t minus 1 is found out by t minus 2 into w plus x into t minus xt minus 1 into u. So input multiplied with u, weight matrix, hidden multiplied with w, another weight matrix, that will give us the current hidden. Current hidden, from there how to get output? You again has to multiply the weight called as v, you get output at t minus 1. That is the current output. Now current output is compared with the actual output. Actually it should have been yt minus 1. You have got ot minus 1. Definitely, if you compare these two, you will have a loss, and that is called LT minus 1. Is it clear? See, if you want to find HT, what you have to do? You should know HT minus 1, XT, but not as it is. HT minus 1 has to be multiplied with W, and XT has to be multiplied with which matrix? U. You get HT. From that, you multiply with V, you will get OT. Actual is YT. OT another predicted. OT minus 1, OT plus 1, they're all predicted outputs. T another time. OT minus 1 is a predicted output at T minus 1. First second, third second, fifth second, either some time. Okay. T minus 1, YT and YT plus 1 are the actual outputs. Now, definitely there may be some differences. So that is, captured through loss. LT minus 1, LT and LT plus 1. Now here, this is a case where the recurrent neural networks that produce an output at each time step. That is correct. At every time step, the output is produced. OT minus 1 is produced at time t minus 1. OT is produced at time t. OT plus 1 is produced at t plus 1. At every time instant, some output is produced. Best example, chatbots, virtual assistants. Every question, some answer will come. And even language translation, something is going to come every time. So at every step, some output is produced. And they have recurrent connections between the hidden units. That is correct. They have recurrent connections between the hidden units. This is the recurrent connection. They're straight ಇದೆ. Only horizontal connections is going on is between hidden. There is a connection from ht minus 2 to ht minus 1. There is a connection from t minus 1 to t to t plus 1, like that. There are recurrent hidden connections. A straight what is going on is a normal connection, but here between the hidden there is a recurrent connection. So there are 2 points in this kind of an example or unfolding. Unfolding case 1 is you are producing output at every time instant. Every time instant some output is produced, and there exists a recurrent connection between the hidden units. There is a recurrent connection between the hidden units. Let us see the second case. Second case of unfolding computation RNN. So what is going on here is, instead of having connections between the hidden units, what is happening there? Previous output is connecting to the current hidden. Now, if you want to find out the current hidden, as earlier, the present input or the current input, and earlier it was previous hidden. Now it is previous output only. Previous output is connecting to the current hidden. Again, with the same weight matrices. For the previous output W are multiplying, for this you are multiplying U, and for the current output you are multiplying V. All these 3 matrices are same, but instead of choosing previous hidden, we are using previous output. Again, at every time instant, some output is produced, whether chatbots or language translation or speech conversion, whatever, text to speech, same thing. All these examples the same, but the recurrent connections are different. So output at each time is same. Recurrent connections only from output at one time step to the hidden units at the next time step. That is correct. Output at the current time step to the next hidden, this output to the next hidden, like that. Third case. So here again, there is a hidden connections between the hidden units only again. The previous hidden, current input, current hidden. Same thing, no change. But what is missing is every time you are not producing output, you are taking that to the last stage. You get chopped over it's the last stage. Until that no output is produced, you will never produce the intermediate outputs. Direct output you are going to produce. Okay, until that nothing is given. Okay, it's like you order for a samosa for a bulk, for example, 100. So they will not bring one by one from the shop. They will do all 100 and finally bring. Other if they are preparing the college itself, every time 5 or 6 is done, they just give there and it can be supplied. So that means you have to wait till the last. For example, sentiment analysis. Entire paragraph you have to read and then finally find out was it positive or was it negative or was it neutral. So one input, one output only. So finally, even though input is given at different stages, output is only one. Maybe final sentiment what it is. You may have to find out. Okay. So what is happening is at every stage input is used, previous hidden is used to find out the current hidden, and this sequence goes on until the last hidden stage where the last input and final output you will get. The actual output you are expecting is y of tau. You got O of tau. The loss is L. Maybe if it is not, you have to update the weights. That is again back propagation happens. So this is a recurrent network with recurrent connections between the hidden units that read an entire sequence and then produce a single output. It will produce a single output. Maybe entire video you read and tell me how many goals are there. I don't want one by one. First goal is done, second goal is done. I don't want. Totally how many goals have been done. You see the video and tell me. Entire thing you have to read. Even though you read it one by one, but final output I want only at once, not at intermediate stages. So there were three different things, different scenarios of RNN computational graph. First is where is the recurrent connections? In the first case, recurrent connection is between the hidden units. The previous hidden is getting connected to the current hidden. At every stage, current input will be always there. Okay. Next is second example, and here one by one output is produced. Second, recurrent connections from output, previous output to the current hidden. There's a currency from output of the previous step to the hidden of the current step, not between the hidden. Output to hidden connection is there. And again, the output is produced at every instant of time. Final output is produced, only one output is produced in the third scenario, but still the existence of the connection recurrency is between the hidden units. Okay. So between the hidden units, the output and hidden units, two cases. And as far as output production is concerned, it can be step by step or single step. It can be step by step or single step. So that three diagrams are expected with the explanations from you for this question, RNN computational graph. And to conclude this topic, there is a last graph also, which is the actual production environment. That is, what is going on is the input to hidden to output, actual output loss. And what is happening is another scenario while training. What they are doing is they are not connecting hiddens, they are not connecting the predicted outputs, they are connecting the actual outputs in the next stage. Till now again, what we have discussed was the hidden of the previous is connected to you, or predicted output of the previous is connected to you. But here, the actual output is connected to you. Okay. So the current input, hidden output, you get a loss. And then the actual output is connected to the next hidden. This is during training. But testing, what they will do is, the problem is with the testing, they will not have the actual output. So they will use predicted output and then connect to that. So they do different connections with training and testing. Since in training the actual outputs are available, so the actual outputs at the stage t minus 1 is used to connect to the hidden at the time t during training. During testing, since actual outputs are not available, the predicted output of the previous step is connected to the hidden of the current step. Predicted output of the previous step is connected to the hidden of the current step. And then training only, the actual outputs of the previous step is connected to the hidden of the current step. This technique is called as teacher forcing. So teacher forcing, they are trying to force the actual output in the training stage. Teacher and the training. Teacher in the context of neural networks is the training stage, where even though you produce something, it might be wrong or there may be some problem. Says that no, this was the answer, use it for the next time. If a training stage, the actual output itself is given. Teacher forcing. So these are all the part of RNN computational graph. So 4 case studies you have to give, 4 scenarios you have to give. Hidden to hidden with step-by-step output. Output to hidden with step-by-step output. Second case. Case 3, hidden to hidden with single step output. Case 4, training actual output to hidden. Testing predicted output to hidden. That is called teacher forcing. So 4 types of RNNs exist. 4 types of RNN connections are possible. 4 types of RNN computations are possible. And they all have to be written or bundled inside a topic called as RNN computational graphs. 4 graphs are possible. 4 computational graphs are possible. 4 ways to compute RNN is possible. Okay, fine. Next comes the gradient. Gradients already we have seen in our regular neural networks. That is basically used during backpropagation. So it is same again. Just like our feed-forward or conventional convolution neural networks, gradients and the derivative of the error, which has got both the direction and magnitude, and direction will tell whether I have to increase the weight or decrease the weight. As we have already discussed those gradient things. Same concept of gradients which was used for backpropagation is used in the RNN also with one change. That is, the gradients are belonging to a step time t. There will not be universal gradient for the entire training stage. At every step t, time, because time is involved in RNN, gradients are time specific. Therefore, what they call is, it is not just a backpropagation, it is backpropagation through time. BPTT, they call backpropagation through time. This gradient you have to do at time t. Next gradient you have to do at time t1. Gradient at a time, not just a gradient. Therefore, it is called backpropagation through time. BPTT. That is one difference between gradients of the normal neural network and gradients of the recurrent neural network. Fine. So, as can be seen, it is time specific. So, what is going on here is x1 is our input, s0 is the previous state. So, you apply w, you get s1. You have to use 2 things to get s1. What are they? Previous hidden multiplied with w, current input multiplied with u. Then from s1, when I multiply v, I get y1 cap and the predicted y1. Actual y1 is y. So the difference between actual y1 and y and its derivative is called as e1. E1 is a gradient of instance 1. E1 is a gradient at the time instance 1. E2 is a gradient at the time instance 2. E3 is a gradient at the time instance 3. Remember, multiple weight matrices are there. Input weight matrix is U. Weight matrix associated with the states is W. Weight matrix associated with the output layer is V. And the hidden layer V multiply, you will get output layer. This is what we can see. Therefore, lot of gradients have to be back propagated. One is gradient with respect to V, gradient with respect to W, gradient with respect to U, gradient with respect to Bs and By. Bs and By and so you can see so many partial derivatives. And you have an error. Delta E is a gradient error, but that error has to be differentiated with respect to V, one of the weight matrix. And the V has to be changed. W has to be changed. U has to be changed. WV has to, there are two biases also, Bs and By. It is a bias with respect to hidden state. By and the bias with respect to the state Y. Input in bias they are not taking. Okay, only with the output layer and the hidden state layer they are using biases. So 5 these things you have to take gradients. Now how to calculate ST? It depends on previous state, ST minus 1 multiplied with W. Then technically they call dot product. Along with that, U into XT, current input, and multiply with U. Along with that, BS, bias. For this is linear equation. How to make it non-linear? Apply a non-linear activation function like tan H. You get ST. ST in the how to get Y prediction YT, V into ST plus its bias. On that you apply a function called softmax. You get a lot of probabilities. You find out which probability is higher by using softmax. Then how to get the error on that? It is minus YT into log Y cap T. It's not just Y minus YT, remember. It is minus YT log of predicted minus actual into log of predicted. This is one standard mathematical way to get the gradient of the error. At the time T. This to at the time T. These are all the mathematics behind it. This is what happens. So at the time 3, what you get is propagated to 2, 1, etc. It goes back propagation through time. And this is how you can calculate the different gradients. Say delta ET by delta V can be written as delta ET by QT into V. And what is QT into V? YT minus YT cap, the predicted minus actual. Now, when you are differentiating with respect to V, these two can be written as YT cap minus YT into delta QT by delta V. Now, this remains as it is. What is delta QT by V? Here is the equations. To differentiate this with respect to V modulo, you get ST into T transpose. Okay. Like that, mathematically, you can compute the gradients. Both gradients are shown there. Bias as well as this V. So gradients in RNN, that is that gradient is calculated. Calculation remains the same. You have to take partial derivatives of all the equations. You have to take the partial derivatives. But one difference is it is calculated at every time T, okay, compared to on the universal training gradients. Next, recurrent networks as directed graphical models. There are two graphical models, directed graphical models. One directed graphical model is from the current output, you get the next output. From the next, to get Y3, it depends on Y2 as well as Y1. Next, Y4 depends on three things. What are they? Y3, Y2, Y1. And every output depends on all the previous outputs. That is one directed way, directed graphical model. The current output depends on all previous outputs. That is called fully connected. Okay, second output depends on first. Third output depends on second and first. Fourth depends on third, second, first, etc. Output at T depends on all previous 0 to T minus 1. And this directed connections are called as fully connected graphical model, where a current output depends on all the previous outputs in the sequence. But this is going to be very inscalable and infeasible solution. Practically, it is very difficult to compute these things because as the outputs increases or the output neurons increases, fully connected becomes a very difficult one to implement. Therefore, they have gone for a much efficient model called as parameterized model, where instead of making every output depends on all previous things, every output you find out hidden state. That hidden state is given to the next hidden state and the next output. So every time only one hidden state is given rather than all of them determining this. To take the help of hidden states, you add one more layer of hidden states. Rather than simply connecting the outputs, they are indirectly connected now. And then the output is connected to hidden state is then connected to the next output. Like that you do it. This reduces the number of connections between the outputs. So this is called efficient parameterized model with the hidden states. So there are two ways. One is you directly connect the outputs, but the problem is you have to connect every output with all the previous outputs, which is an inscalable solution. Second thing is every output you connect to hidden state, which will connect to the next output. Okay. Like that you make a sequence. That is also a recurrent network. So two solutions are there. Last part today is modeling sequences. What is sequences is rather than giving a single input, you can give a vector of input. Rather than just giving one character or one word, you can give the vector of words. That is called sequence. Instead of always using input and making it as a single input, till now what we have used is a single basic unit of input. You can have a vector as an input. Okay. So if it is a vector of input, it is called as sequence. So there are two ways of using this. Whatever vector is there, the same vector you give to every hidden state. Earlier what you did was, you made your input, divided it into multiple pieces, and you gave it at every stage. Now we form a vector of input. And instead of the thing is, instead of giving the text directly, you calculate embeddings. Embedding is a vector. That vector is given to all the hidden states, rather than giving every time that different inputs. You compute the embeddings and give that same embedding to every hidden state. Instead of giving a part of the input, you give complete input. Instead of dividing input and giving piece, you give complete input as an embedding or something, and that is called as a sequence. So fixed length sequence it is. So give that fixed length sequence to each hidden state, and the other things are same. Okay. So this is called single fixed length input vector strategy. Okay. What is the next strategy? Instead of using a single fixed length, you partition that vector into small subsequences. If you can't give a single sequence, you partition them into subsequences and provide subsequences like this. See, subsequence are you will use a weight matrix U, whereas single sequence means you will use the matrix R. Diagrams are different. Both strategies are there based on the application we do. Whether you are doing language translation, whether the text summarization is done, all these things happens behind the scene. One more thing is, as a programmer, you may not feel it always because you'll be using a lot of black box APIs. But behind the scene, these models will be there. These strategies will be there. Input might be divided like this. Input might be vectorized and given fixed length. Or input might be divided into small vectors called subsequences. Okay. Different strategies are there when RNN is being used. Okay. So that completes the modeling sequences. Conditional RNN with variable sequences of input. Okay, I think then we will discuss in the class itself bidirectional RNN. So in this video or the online, what I discussed today is these things. I would like to summarize. First is some basics of RNN and its comparison with CNN and its applications. That is one question or one part. Second thing is writing the computational graphs first in the case of basic feed-forward networks, then for RNN. Third, RNN computational graphs, 4 scenarios we have taken. 4 scenarios. Hidden to hidden recurrent connection with step-by-step output. Output to hidden recurrent connection with step-by-step output. hidden to hidden recurrent connection with single step output. Output to hidden during training, actual output to hidden during training, and predicted output with hidden during testing. This is one more case. Four different cases were taken. And then we have also seen something called as gradients, how the gradients are computed, the equations, and how it is different through a concept of BPTT, back propagation through time, rather than simply back propagating same thing again. It is back propagation at the time t. That was being discussed. And then, the recurrent networks are the directed graphical models. Two different cases were taken rather than one is fully connected. One output depends on all previous outputs, or use the hidden state and make it much efficient, which is called parameterized mechanism. And finally, at the end, I discussed on sequences. Rather than using inputs as single units, use inputs as sequences. Either use it as a fixed length vector or variable length subsequences can be used. All these strategies apply in RNN. Now, next class, we'll be seeing what is bidirectional RNN and what is LSTM, what is GRU. These are all the building, what we can say, pillars, building blocks of RNN. If somebody asks you what is RNN, do you know something about it? All these are expected to be known. Resume you put some project, have done on RNN or something. Basics will be asked always. Okay, so little basics. You know that the advantage is you can apply to something else also. That will be the confidence they get if you can answer that. So these basics, please learn it properly, so that whenever you next appear for any other career advancements, it will be helpful. Okay, thank you then for giving this time. I'll stop here.